Hello everyone, myself N. Udayaranjan Gaud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous class, we have discussed about the introduction class of stress analysis of aircraft components, wing and fuselage, in which we have seen the module 1 as wing tapered wing spar as well as the box beam. And now we have derived the relationship even for the web shear flow, how to calculate the web shear flow for a tapered wing spar. Now let's use that formula which we discussed in the previous session, and we'll try to solve problems in the present session, which is problems on tapered wing spar. And then the learning outcomes are nothing but solving the problems of tapered wing spar here. So let's try to find out this. Now let's consider this question. Determine the shear flow distribution in the web of the tapered beam, which is shown in figure, at a section midway along its length. So the web of the beam has a thickness of 2 mm and is fully effective in resisting the direct stress. The beam tapers symmetrically about its horizontal central axis, and the cross-sectional area of each flange is given as 400 mm square. Okay, so he has given the tapered wing spar that you can see in this diagram, and then he is asking to calculate the shear flow distribution in the web of the tapered beam as shown in figure at a section midway along the length. So at this section at AA. So at this section AA, and he has given the cross section over here in the second diagram. So the section AA, if you look at this one, so there is one boom here, that is boom 1, and here one more boom is there, that is boom 2, and the panel depth is nothing but 300 mm that you can see at midway. Here it is 400 mm and here it is 200 mm. So at the midway it will be 300 mm because it is following some linearity, and the thickness of this web is also given, that is 2 mm. Okay, and then the cross sectional area of each flange is given as 400 mm square. So the boom area you can consider it as 400 mm square. So this is section AA. So first a tapered wing spar is given, and which is of 2 meter length, and he's asking to calculate the shear flow distribution at the halfway, okay, or midway along its length. Okay, so this is a question that is given. So tapered wing spar. So that one thing we understand here, and the previous analysis what we consider the wing spar like this. Okay, we consider the wing spar like this in the previous derivation, in which we derived the formula, and we have assumed this as delta y1, and we assumed this as delta y2. Okay, now here we consider the taper as positive. That means when you draw a tangent, and the taper we took onto the upper side, and whereas from here we took taper onto the downside, and we consider this as negative taper. And then we assumed P1 as flange load here and P2 as flange load here, which has components PZ2 and PY2, and similarly here it has components here horizontal axis, that is PZ1, and vertical component we got PY1. Okay, so this is a derivation which we considered, and if you try to extend that analysis here to the diagram which is given, it's quietly opposite diagram. Okay, because we got a taper over here on the left side, but here if you look at the diagram, we have taper on the right side. Okay, and also, and if you consider from here the horizontal axis, the taper is taken in the downward direction, whereas if you consider here, the taper is taken as the upward direction. So slightly the sign changes will be possible here, either plus or minus. So how to see that one is nothing but, so we need to consider this force P1 as force in flange 1 here like this, and then if you try to resolve into components, so this will be horizontal component PZ1, and the vertical component will be downwards instead of upwards, and we'll get here downwards. Whereas for the second one, if you assume P2 as the load, axial load in the flange 2, and then the horizontal component would be PZ2 here, but the vertical component acts upwards. Okay, but here vertical component here Py1 is upper side and upward direction, and Py2 is downward direction, whereas here Py1 is in the downward direction and Py2 in the upward direction. So that is what the changes what we get from this derivation and the formula what we get. So plus or minus changes may be there according to the formula. Okay, So let's look into this problem. So the internal bending moment and the shear load at this section A produced by the externally applied load are respectively. So if you look at that bending moment mx at that section, so here we got section 1 and the load he has given 20 kilonewton, so which gives moment about this AA. So the bending moment mx is equals to 20 into, and this perpendicular distance is nothing but 1 meter. So 20 into 10 to the power of 3 into 1 meter is also there. If you try to convert into mm, then you are going to get another 3. So you can write this as 20 into 10 to the power of 6 Newton mm is the bending moment that we got. Okay. So here, so 20 into 1, that is 20 kilonewton meter is there. And if you try to convert this in, and again you are going to get 20 into 10 to the power of 6 Newton mm. Okay. And the vertical shear load is given, that is acting downwards. So we have to assume Sy equals to minus 20 kilonewton. And then if you look at the direct stress distribution formula, and we got Ax plus By, where A equals to My Ixx minus Mx Ixy divided by Ixx Iyy minus I square xy, and constant B is nothing but Mx Iyy minus My Ixx divided by Ixx Iyy minus I square xy, in which you can substitute the product of inertia as 0 and you can substitute the horizontal shear load as 0, so that this constant A becomes 0 and constant B becomes, you get Sx by Ixx. Sorry, Mx by Ixx. Okay. So when you substitute in this equation, you are going to get sigma z equals to Mx by Ixx into y. So for a symmetrical diagram in which Ixy is 0, Sx is 0, the bending stress distribution formula reduces to Mx by Ixx into y. And you can assume this as equation number 1. So now, in which now we are going to calculate the moment of inertia for this problem. And for this problem, if you try to find out moment of inertia for this one, especially for panel 1-2. So panel 1-2, first you have to write the moment of inertia because of boom 2 and it is symmetrical. So if you try to write for this one, for 1 and O, then you get boom area, that is 400 is BR into YR square. So 400 into this distance is nothing but half of this distance. So 400 into 150 square, like that you got 2 booms. So the moment of inertia due to booms is nothing but 400 into 150 square into 2. Okay, that is the boom area here. Now next you have to write for the panel also, that is panel 1-2. Okay, so when you try to write for panel 1-2 and so panel 1-2 is having thickness is nothing but 2 mm, that is the width we considered, and the depth is nothing but 300 mm. So for that you can write apply BDQ by 12 plus A into Y bar square formula. So if you try to write that 2 into, or in fact here we written, so 2 into 400 into 150 square, that is for booms, and for panel 1 to BDQ by 12 you can apply, so which is nothing but 2 into 300 cube by 12 plus area, if you write 2 into 300 and its Y bar is 0 because the total figure centroid and the centroid for this 1-2 coincides on this axis. So therefore that will be 0, and therefore you can write moment of inertia as Ixx equals to 22.5 into 10 to the power of 6 mm power 4. Okay. And once you get this Ixx, and you can substitute in this formula, so that sigma x is equal, sigma z equals to, and mx is nothing but 20 into 10 to the power of 6, you can substitute, and into y is nothing but the distance, maximum distance from neutral axis, which is nothing but 150. Total depth is 300, and out of that half of the distance will be 150, which is maximum from the neutral axis, and divided by the moment of inertia, that is 22.5 into 10 to the power of 6. And when you try to calculate this, you are going to get 133.3 Newton per mm square, and then you can write this as sigma z1, that is equals to minus sigma z2, that is equals to 133.3 Newton per mm square. Okay, so sigma z1 is nothing but that is the horizontal component of flange 1, and that is force 1, and then sigma z2 is nothing but the horizontal component of axial load P2. Okay, so these are the stress resultant, which are bending moment, bending stress resultants. Okay, so once we get this sigma z1 and sigma z2, and then we can get the other values also. So sigma z1 and sigma z2, we got the stresses, and let's try to calculate pz1. So PZ1 that is equals to minus PZ2 that is equals to what you can get is 133.3. So forces, already we have stresses, so you can multiply the area so that you can get the force resultants also 133.3 and the area. And the area of each stringer he has given 400 mm square, that you can substitute, and then you get PZ1 that is equals to minus PZ2 and it comes to 53320 newtons. Okay, so that is PZ1 and minus PZ2. Right, now coming to shear, and the shear load resisted by the beam is then, so SYW, we have seen the formula, SYW that is equals to SY minus PY1 by Py1 divided by that is Pz1 into delta y1 by delta z, or Py1 you can write in like this only, and then minus Py2, sorry, this formula you can write this Pz1, so Pz1 into delta y1 by delta z, and you can write this as Pz2 into delta y2 by delta z. Okay, so that is a formula which we written from the previous case. Now for this case, what you can write here it is, and if you look at this one, the formula slightly differs, and what here we got is, if you look at the diagram, and if you look at this diagram and the taper, basically taper, we are trying to look at the taper. So the taper here is and even if you try to see the components, this is P1, and here the vertical component Py1 will be downwards, and whereas Py2 will be in upward direction. Okay, and even if you look at the taper, so taper also delta y1, this is delta y1 and this is delta y2 taper. Okay, delta y1 is downwards and this is upward taper. So therefore slightly the formula modifies here, and instead of here minus sign, and here for this case you will get the plus sign. Okay, delta y2, because earlier that was negative and that will be positive only. So therefore you can consider SYW equals to first SY minus 20 kilonewton, and then the PZ1 that is 53320 into delta y1 by delta z, and 53320 into delta y2 by delta z. Okay, and so this is the formula what we got from the previous analysis, so that we are writing as it is, and then now trying to write for delta y1 by delta z and delta y2 by delta z from the diagram. So delta y1, as we discussed, delta y1 by delta z, so delta y1 by delta z would be, so, and if you look at the diagram, delta y1, so delta y1 is nothing but this one is delta y1. So total depth is 400 mm, and you subtract this 200 mm, so the delta y1 will be nothing but 200, but what you can consider here, it is half of the distance only you have to consider. So from here to here 200, and then from here to here it is 100, so 200 minus 100 would be, so 100, so delta y1 will be 100, and delta z you will consider from here to here, so that you can consider as 2 meters, so you can substitute as 2000 mm. Okay, but what I am trying to write here it is, so this taper is taken downwards. Okay, so that you can consider this distance as minus, whereas for delta y2 the taper is taken in the upward direction from this horizontal axis, so delta y2, so this you'll take it as positive. So with this one we are going to calculate delta y1 and delta z as delta y1 equals to minus 100 divided by 2 into 10 to the power of 3, and delta y2 by delta z, that is equals to plus 100 divided by 2 into 10 to the power of 3. Okay, both you get 0.05 minus 0.05 and 0.05. So when you try to substitute delta y1 by delta z here, and you are going to get SYW, that is the web shear flow, minus 20 to 10 power 3 plus 53320 into 0.05 plus 53320 into 0.05, so which you're going to get as minus 14668 newtons. Okay, so once you get this shear flow distribution in the web, and then you can start finding the shear flow distribution. So the formula for shear flow distribution, we know it, that is the QS is equals to minus SYW divided by IXX and integral 0 to S TD into YDS plus what we got is BRYR. So this is the formula what we have. Okay. So now that we are substituting, so minus SYW. So SYW is minus 14668, substituting here. So minus into minus becomes plus 14668 divided by IXX, which we got it as 22.5 into 10 power 6, and then 0 to S, and this is important, the distribution 0 to S. So this is 1, this is 2 in the AA section. AA, if you look at it, so the thickness is 2 mm and then the total depth is 300 mm. So half of the distance will be 150 mm. Okay. So what we'll try to consider, we'll consider the distribution S1 like this. Okay. So when you try to consider the S1 distribution like this, so from the centroidal axis, you have to find what is this distance. So total depth would be 150 from here to here, and 150 you have to subtract this S1 so that you will get the distance from the centroid up to the section S1. Okay. So this distance would be 150 minus S1. Okay. So therefore in place of Y you have to substitute 150 minus S1. So and thickness is nothing but 2 mm. So 2 into 150 minus S into ds plus BRYR. So boom area is nothing but 400 and its Y distance from the centroid is nothing but 150. Okay. So now integrating this, and 2 you can take common outside, and then one integration of this you can multiply. 150 becomes 150 into S, and S becomes S square by 2. Okay. And then 2 into 150 it becomes 300, and 300 constant, you get 300 into S, and then you can multiply this 400 into 150 as 60,000. So you got Q12 distribution, that is equals to 6.52 into 10 to the power of minus 4 minus S square plus 300s plus 60,000, this we got. So this is a distribution. Now after that what we are going to do is, we are going to substitute the boundary conditions and find out what is at 1 what is the shear flow, and at 2 what is the shear flow. So since S1 is starting from boom 1, so what we can consider here, it is at 1 S1 is S1 equal to 0. So when you substitute in this equation S1 equals to 0, so what you are going to get here, it is when you substitute S equal to 0 here, this becomes 0, this becomes 0, and you are going to get Q1 is equals to 39.1 Newton per mm. Okay. And at 2, S1 distance at 2 is nothing but S1 equals to 300 mm. When you substitute this 300 mm in place of here, again you are going to get Q2, that is equals to 39.1 Newton per mm. Okay. And if you want to calculate at center, that is O, at O, and what you can substitute is, you can substitute S equals to 150 mm. Okay. You can substitute S equals to 150 mm, so that you are going to get 2, that is Q naught at the center. Okay. So at the center, if you try to substitute, then you are going to get the maximum shear flow, and that is equals to 53.8 Newton per mm. So at 1 the shear flow is 39.1 we've written, and at 2 also the shear flow will be 39.1, and these are linear. And then at center you are going to get the maximum shear flow, that is 53.8, and this you get the parabolic curve, so that the parabolic curve can be drawn here like this. So this is the shear flow distribution in the web. Okay. So complete web shear flow distribution that we have to draw here, and that is the tapered wing spar shear flow distribution. Okay. So next, for example, if you have beams having variable stringer areas, sometimes beams will have variable stringers. Now in the previous problem we considered the stringers are similar, same area. So if you have variable stringer areas, in many aircraft structural beams such as wings and have stringers whose cross-sectional areas vary in span-wise direction. So the calculation of the shear flow distributions in the beams having variable stringer areas is based on an alternative method for the calculation of the shear flow distributions. So the stringer loads PZ1 and PZ2 are calculated at 2 sections, that is at Z1 section as well as Z2 section of the beam, at a convenient distance apart. So we assume that the stringer load varies linearly along its length, so that the change in stringer load per unit length of the beam is given by delta P, that is equals to PZ1 minus PZ2 divided by Z1 minus Z2. So we'll consider this for the variable stringer areas. We consider delta P like this, and then we'll extend the analysis like the previous procedure. Okay. So that's all from today's class, and let's look into the next session, that is the shear, that is the bending effect when it comes under stress analysis because of the bending. Okay. So thank you everyone.